Is there anybody who can't hear me? Wave if you can hear me. Wake up, Joe. Isaac's there. Sam's there. Elijah's there. We're good. Okay. So I just wanted to go back just a little bit of examples. It's not new information, so you don't need to take notes on it if you already know. Hello, roommate. It's like I'm doing some magic trick in there. Jack, come on. Really? There's a roommate going, oh, she can hear us. I actually can't hear you because you're muted, but I can see you. All right, let's go over this independent versus dependent variables. If I was studying, okay, let's do this. Let's say that I take some plants and I'm playing music for them. So I have somewhere no music, somewhere hearing classical music, and some are hearing old school hip hop. And I was checking to see how fast they grow. Which is the independent variable and what's the dependent variable? I'll take a volunteer for this one.
The independent variable is like what type of music you play them?
Yep. And somebody else, dependent, let's get somebody else in.
Okay, no worries.
Elijah, you got it? You're muted, Elijah.
Sorry. Would the dependent variable be the people or what they hear?
No. This was plants growing, and the independent variable was what kind of music they hear. They're plants, not people. I think you probably misheard. And then how fast they grow was what we're measuring. So you have a different answer, or should I skip you?
Would the dependent variable be their growth rate?
Yes. And the sample are the plants themselves, which you thought I'd said people. So the sample and the dependent variable are very, very often confused by students, and I honestly don't quite know why, but they are. So I can ask you to identify independent variable and dependent variable when I give you a statement about research like I just did, and you're going to try to not answer the sample for one of those variables. So one way to look at it is who's in the study? That's your sample. In this case, who's in the study? A bunch of plants. What did the experimenter manipulate? The type of music. That's the independent variable. What were we measuring? The result, the growth rate. Look at it another way to see if you have confused the independent and the dependent variable. See if it makes sense. Is it possible that music could affect growth rate? Sure, it's conceivable. Is it possible that growth rate will affect which music they're in? No chance. That doesn't make any sense. So when you have one, double check by reversing your answer. Because I'd say about a quarter of students get this wrong at the beginning of this course. You're just not exposed to it enough. So you might want to look for some practice problems on that online. I'm going to post a file. It's good. I think it's called practice or review for exam 1, but we haven't gotten to at least half of it. The hard part, we haven't started yet, but there will be some questions to practice on it for independent and dependent variables. I don't think I have a practice sheet just for that one topic. I'm going to double check. But what I get is I have student assistant generated practice problems. So once in a while, you might find that it's wrong. If you get a different answer and you think you know what you're doing, and then you get a different answer when you do it again, let me know, because there's a chance the answer sheet's wrong, but there's probably only about 2 wrong answers all term. But we'll find them, we'll fix them. But this one, independent and dependent variables are, that's what it'll be. I'll be asking 3 to 4 questions and ask you to identify the independent variable and the dependent variable. Would it help you if I also asked you to identify the sample and then split up? You get 1 point for each of those. The only reason I'm asking isn't to make it harder so that each one would be worth 3 points, but to, if you put the sample down, if you have to put the sample down, it'll help you know that it's not one of the 2 variables. It's just, think about it. We can talk before the exam. You can help make this, you can help design this exam. Okay. So I just wanted to review that. There's plenty of practices on independent versus dependent variables online. Just find one that you like. That's the trick with teaching and learning online, is that I'm going to just, instead of being in my office and pulling out a stats textbook at random and saying, here, let's see some examples, you get to find them online. And if you don't find one you like, let me know and I'll track some down. I'm probably going to do that for all of our problems. And the reason why I don't just do it all the time ahead of time is because these pages aren't stable. They aren't all staying online. Sometimes it's a student's project and then it disappears when the course is over. So I've given up trying to keep a good list for now. More and more are showing up now though, because more and more people are teaching online. So we have more information, but it's not stable. Okay. So what I covered since that topic was scales of measurement, frequency distribution tables, and graphs. First, let's talk about the homework. Any troubles? I believe one person at least told me that they were having trouble with the frequency distribution table. And did anybody else feel like they weren't quite sure how to do some of those columns?
I had a question.
Yeah.
Like relative frequency, I think that was the one. Does that always have to equal 1?
Yeah, at the
Yeah.
bottom or close to it, Jack. So sometimes because of rounding, you'll get like 0.98 or 1.02, but it doesn't usually get further away than that ish.
Okay.
What did you get for relative frequency total on this?
I think on the second one, I got like 1.01.
Yeah, that's common. Did anybody else remember getting that? I see Sam nodding, so.
I Googled it because I got nervous.
Yeah, it happens. It's ideally 1, but rounding is what's causing that. Any other questions? Right, we can do a private session for anybody who's having major issues with it. I don't mind that at all. We can do it right after class.
Wait, I do have one question.
Yeah.
What is N?
Oh,
forgot
I'm sorry.
what
No, because I forgot to tell you guys. N is a number of people total.
Oh, okay.
Oh my gosh, I can't believe I forgot the most basic data that we collect, N. You know, in some cases, people will use a capital N to indicate a population and a lowercase n to indicate a sample, but in this course, we're going to use it, but we're not going to be so fussy. Because there are some examples that where we're actually working with a population and some where we're thinking about samples. So we're just going to go N, whichever way we do it. I like to write it as a capital N. It's easier to see in a formula. Sometimes when I write it as a lowercase n, my lowercase n looks like the letter mu. And so it looks like I'm saying get the population mean. And so people get very confused. Okay, so anybody else who wants some deeper help with this, either email me or stay right after class and we'll take care of that. Either schedule another time or just do it right then. Okay, graphing. There were rules. There's label your axes. There's the 3/4 rule. There's the y-axis has to start at 0 rule. Those are the 3 biggies. So I have some examples here that I'm hoping you'll be able to see. that are bad graphs, very bad graphs. I'll be curious to see if we can do this. I can't see myself very well, but okay. Can you see this graph pretty well? There's going to be two more just like it to look at, but this first one, it's got issues. So who would like to tell me about, yeah, okay, and now I can see my own. Who would like to tell me what's wrong? We actually, let's just start. I'll go through them. Are the axes labeled? No, one is, the vertical axis is labeled. Those are billions of dollars. And the horizontal axis is not labeled, but somebody will figure out what it is shortly. And when you do, tell us what you get.
The months of the year.
Yeah, months of the year. C, J, F, M, A, months of the year. Why they didn't label that is beyond me, because there are plenty of people who could sit with that for quite a while and not realize that it was months of the year. Okay, so that's one rule that was broken. What's another rule that was broken?
The 3/4 rule.
Yeah, the 3/4 rule. This looks like it might be a little bit taller than it is wide. It's supposed to be 3/4 as high as it is wide. So it should have stopped, the whole thing should have gone maybe to right there-ish. So not only is that too tall, but look where all the data is, all above the 3/4 point. Which takes me to the next one. Does anybody have anything to say about the next part that's been broken? I don't think I mentioned this rule, so I'm just going to give this one to you. There's a 0, but it didn't use the whole axis to display the data. You're supposed to set up the y-axis so that you only include numbers that the data need. So these data apparently start at or just below 20. Is that a 20? My screen shows it backwards. At or below a 20 and ending at about a 22 or 22 point something, right? It's only going across $2 billion as opposed to a total of $24 billion. So the graph should be more numbers like these, because that's the range that you need. So maybe one way to say this is the y-axis needs to include a 0, but the rest of the numbers should only be covering the range of the data. Who has a question about what I've just been talking about? Who wants it explained another way? You must speak up, or you will just go along for the ride in this course and we'll see what happens. Okay, now, so that's what's wrong with this one. Consequently, we have this stupid looking little guy back here who isn't part of the graph. It's just to show you that he's happy. He's happy and he's following an upward trend, right? So, and it's all very high. It's all really good numbers, unless it's about spending, but he's happy. So it's probably about some, like Apple's income that year, right? Okay, next graph, same guy, same data. They're not having the problem with the range. Label axes, same problem. Look at the 3/4 rule issue. This is more of a 1/4 rule. This is like 1/4 of the y-axis is about 1/4 of the x-axis. And consequently, you get a very different feel. First of all, it doesn't look ridiculously high. So you're not trying to influence people. People love to influence with graphs. Our old president, Meyer, here at the college, who Meyer Hall's named after, is kind of famous among faculty for creating graphs for the Board of Trustees that made everything look really, really great all the time. And he never followed the rules, the three-quarter rule. So we would get graphs in all different shapes when he practiced in front of us at a faculty meeting. And everybody who teaches math would just start cracking up and he would get really mad at us. And it wasn't pretty, but it was funny as hell. So, okay, well, here we go. We've got reasonable. He's got an extra 2 billion in each direction. What happened to the zero? Missing. I know it's dumb, but you're supposed to include it. I know it feels ridiculous, but you're supposed to include it. Why? I'm actually not sure. None of us are anymore. It's like tradition now. So the data are looking like they're rising at about the same rate as these data make it look, but it doesn't make it look like it's all really, really great by putting something up very high. It actually just looks like nothing like that at all. All right, next guy, hold on. These are just copies, don't worry, I don't have pages and pages. I gotta get this guy, he's folded in the middle, so. I was gonna do a PowerPoint and make a screen for each of these, but to be honest, I really hate that, so. Okay, first guy, second guy, now, third guy. It's sort of the same guy's face, but not really, because look at his eyeballs. They're trying to tell us something, I don't know what, by his face. So it's weird, but okay. Axes labeled, same problem. Only one is labeled. Zero there for billions? No. In fact, these numbers of billions of dollars are probably more useful. It's breaking it down a little finer, 20, 20.5. Hold on, I can't see it. Oh, 20, 20.2, 0.4, 0.6, all the way up to 21, all the way up to 22. It's a better measurement of numbers that range from 20 to 22 is to break it down more finely like this. But that said, the three-quarter rule isn't being followed. So it makes the data appear to be inclining faster than it is. It's very misleading. Each of these three graphs is quite misleading. The top one is pretty useful because it's not breaking down what's happening between 20 and 22, and it's all just smashed into some little part that's way up high. This one is also not useful because, again, it smashed all the data into between a tiny little range and you don't get to see any differences. Whereas here, pretend this is sales. Sales in January, February, and March and April keep increasing. It slows down in the spring and summer. And then it increases again all the way through to December. That will help you create some policy or action at whoever's trying to sell these billions of whatevers. Right? Without that fine breakdown, you don't get the data that you need to use to work. I mean, why would you collect the data if you're not going to use it for something? And by collecting it this way, where it's fine-tuned, you're able to get more use out of it. The problem with this one is because it's square and not the three-quarter rule, it makes things look like they're more dramatic than they actually are. All right, that's those three graphs. I'm going to move on. Okay. I call these whole things gee whiz graphs because they're all trying to impress you somehow. this is two different graphs that of the same data, enrollment in higher education as a percentage of the population of 18 to 24-year-olds. And this is old stuff. It's data that was collected for a historical purpose. So it goes from 1950 through 1970. Okay, so this is some history person who put this together. And then they included it into a textbook, an education textbook. Okay, and I found it. So the first one over here on the left, these are the years. Sorry, I'm not holding it well. These are the years. And the vertical axis is the percent of population enrolled in higher ed. Can you see it well enough to tell me about what percentage of the population in 1950 of 18 to 24-year-olds, what percent was in higher ed? Somebody call it out for us.
14.9%.
Yeah, that looks right to me. So what Elijah's doing is he's going to the 1950, which is all the way over to there, and he's looking at how high up they are, and they're at 14.9-ish. We don't know because it's not broken down finely enough, but it's a good estimate. Okay, and what we can see is that it then declined slightly in 52-ish, and then there's been increases with some more increasey than others. This increase was faster than that increase. Right, there's some areas where it kind of flattened out, not quite, it increased, but this is a faster increase. Okay, so let's talk about the rules on this one here. What's wrong, what's right?
No zero on the y-axis.
No zero on the y-axis. A student who was holding on to this sheet decided the same issue. What else do you have?
The x-axis isn't labeled.
Isn't labeled. You're supposed to label it even when it's obvious, because don't forget, people are going to be reading this of all levels of education, from all native languages, and we need all the help we can get. Also, this is what's called a legend. It gives you an idea of what the graph's about. If you include a legend, you don't have to be quite so specific sometimes with your titles on your labels on your axes. In APA style, you need to provide what we often think of as a title for the graph, but a title is just another name for a legend. Okay, and sometimes you do what this style is, sometimes you include a note at the bottom of a graph in APA style, and you'll see articles with that. Okay, so we have a label problem. What else? Oh, come on, help us get through these.
The 3/4 again.
Yeah,
It's
thanks.
like a
You
square
can just
graph.
keep saying that for the rest of class and that'll be good. Okay, so we'll just make that your job. What's your shirt say? Quarantine what?
It was for a fundraiser, just quarantine 2020.
That's good.
Yeah.
Okay, so we can tell that it went down and then it went up, but we have a 3/4 rule problem. So the angle of the graph may or may not be close to what really was, what it feels like. The feel of this, look at just the feel difference between the two. We're going to definitely have to deal with this issue, but doesn't that feel like there was a more dramatic increase in percentage of people in higher ed? Right, so this is why we have a 3/4 rule, so that we stop lying with statistics. One of these is really overestimating and the over-presenting, and the other one is under. If you follow the 3/4 rule, you would be squeezing all the data on this graph into about that space, no, about that space. And it would look a lot more like this. All right, so that was 4 and 5. Now we get to my second favorite one. This one wasn't intended to be a great graph. This one was found in an annual report from Time magazine, who is trying to tell its shareholders that that the advertisers who in the area of consumer services, insurance, financial advice, things like that, that those advertisers prefer Time over Newsweek or US News for advertising. That's good news, and that's trying to convince the board and any potential funders that that Time magazine is strong. Okay, so take a look. They don't label the axes, even they don't even have axes, but this is, think of this as the x-axis sort of, and this is the y sort of, but really it'd be in closer like that. And because it's for a slick presentation and not an academic presentation, you don't get labels. That's common. You just have, they're inferred. And these are bar graphs. So it's the last ones that we've been looking at are line graphs. This is a bar graph. The same data, they just present it with bars instead. All right, there are many problems here besides the labels not being there. So US News has the lowest number of dollars being spent. Hi, honey. The lowest dollars being spent on that kind of advertising. And then, who is it, Newsweek? And then Time. Time's doing great. Look at them. Look how strong they look. Okay. How much higher pen-wise is Newsweek from US News? Is it almost twice as high-ish? Not quite twice as high. Okay, now look at the numbers. We have US News is 1.5 million and Newsweek is 2.6 million. So are those numbers about, do the heights reflect that okay? I think it's close. And then you have, between Newsweek and Time, you have 2.6 or 2.7 million and 4.4 million. Again, I think the heights reflect that pretty well. The bars are about the right height. Why does Time look so much stronger? If you ever learned about bar graphs, you might remember there's one rule that we actually haven't talked about because I wanted you to learn more about line graphs, but
Do they need to be the same width?
they sure do. And when they're not the same width, they present this kind of an issue. So how many, if this is imagine that these are containers and you're pouring water into them. How many of the little US News pens worth of liquid could you fit into the Newsweek pen container? How many of those little vials of US News water could you fit into the Newsweek vial? About. What's your best
Look
guess?
like 3.5 or 4 even.
3.5 or 4. But we already talked about these two numbers, and this one is twice as high.
Yeah.
There's twice as much advertising dollars, not 3.5 or 4.
Mhm.
And the difference between these two is hysterical. So the small one is 1.5 million. The top one is 4.4 million. That's about 3 times as much advertising dollars. How many little pens worth of water can you fit into the Time pen, the big one?
More than that.
A very big number.
Yeah.
Like 10, 12 maybe. It makes it appear, this is cheating. It's cheating, and this is lying with statistics, beautifully done. This is what our president used to do, and we used to tell him it was an embarrassment, and he used to say, well, no, I think it represents things nicely. We're optimistic. Okay, fine. So we just gave up. So this makes it seem as if time is getting tons and tons, maybe 10, 12 times as much advertising dollars, when in fact it's 3 times as much. Cheating, lying with stats, one of the best. All right, now we have the dumbest graph of all. This is the worst graph I've ever seen ever. I've kept my eye open trying to find a better one, but I can't. The writing on this one is terribly small. It is going to be, here's the legend. Chart indicates rise in state and local property taxes over 12 years. It's from the Bureau of the Census. I just realized I don't have to keep turning them around. I have a second one I can look at. I'm not fast with this Zoom stuff. Okay. All right, so let's start with the rules. Labeling axes. One is, one isn't. The one that isn't, again, it's obvious, it's years. 3/4 rule? No, it looks like they tried more. I don't know how it's showing up on the screen, but it's at least a little bit shorter. The vertical axis is a little bit shorter, but it's closer to square. But it's in the right, that's the only thing in the right direction, but it's in the right direction. Okay, start telling me what else is wrong with this. It's just wrong. It's like really bad.
Are the axes like reversed? Like should the years be on the bottom there, or does it matter?
Like that?
Yeah, I don't know. That looks more natural.
Yeah, it looks, yeah, because putting years in a vertical, I've never seen that before, and it's odd, especially when you're putting billions of dollars in the horizontal. Dollars and make more sense in the vertical, and we're used to seeing years on the horizontal. That's just kind of a standard look. So there we go. And now the 3/4 rule is really shot now, right? Now we have like the 1 1/4 rule. Okay, there's plenty more with this of bad things with this graph. You have to pretend you can read those numbers even though they're backwards.
What's going on with these lines here?
They don't even match up some of the time.
Like that? Is that
I
something
don't.
above our pay grade, or?
I think it kind of is, but I think the intention is just to help. I think they thought they were helping your eye follow data up from a certain year and across from a certain amount of money. I think they did that to be visually easier. And it didn't help at all, right? It just looks like you're supposed to understand something. Just like you said, it looks like it's above our pay grade, that there should be something we know that those lines are about. But I honestly believe they were just visual, supposed to be visual helping. All right. Good news. The y-axis, which is billions of dollars, starts at 0. First one we've had today. Okay, talk to me about this horizontal axis.
Why do some of the numbers, I can't really see it. Okay, so like it goes 19, like some of them just say 1940 and then some of them say 1964 to 1965. Why would you say it like that?
Beats the
Why
hell
would you
out
just
of
keep the same increment
Yeah,
all
so
the way
the
up?
increments don't stay the
There's
same.
also not really a pattern. It goes like 40, 42. So it sounds like it's going up by 2s and then just like skips like a bunch of numbers and goes
I
up by 2s,
know.
skips a bunch. And then it's
It's
like
like
69, 70. So it doesn't have like a pattern.
it has a pattern. They keep going up. It's in the ordinal scale, but time, years, is actually in the interval scale. There should be equal intervals, but instead, the first gap is 2 years, then 2 years, then 2 years, then 4 years for the same, between 46 and 50. It's the same amount of space on the graph, but it's double the amount of years. And then it just gets weird. Then it's 4 years, 6 years, 2 years, some combination of 2 and 3 years, etc. I mean, it's just ridiculous. Okay, so the best way to actually look at this graph, if you wanted to see it in the way that it was actually should have been made, this is hard. You have to look at it backwards, like hold it up to the light like that. That's actually following the way that you would orient it if you were doing it right. And the intervals are really off, but what it ends up telling you makes sense, is that we're paying more taxes as time goes on. Taxes have increased, property taxes. Now, this unbelievably badly done graph, here's my favorite part. The source is the the Bureau of the Census. Government spending to create this, which got published everywhere. Like this was everywhere. Can you imagine your tax dollars at work, or at least mine? Unbelievable. So that's why we have the rules in graphing. If you have the bars separate, I mean, if you have the bars on equal widths, you get to really influence people. If you don't follow the 3/4 rule, you get to really influence people, et cetera, et cetera, et cetera. It can be really messed up if you don't. That's why we have agreed upon. So the rules aren't required by the math. The rules are required because as a math culture, people who create this stuff, as that culture, we've agreed to present our data this way. We've agreed that there should be some consistency, and this is the consistency rule. These are the consistency rules that we agreed on. Does that make sense? So when you look at graphs, if you ever see any in articles, or especially if you see them in like newspapers and websites, look and see if they're following the rules. And if they're trying to convince you of something, there's a good chance they're not. Some data is just dramatic enough that it works well with the rules, but if somebody's desperate to get you to think or believe a certain way, they'll stretch these rules. Okay, so that's graphing. I'm gonna move on to another topic, which is measures of central tendency, because here's where it fits into what we're doing in the course. We have so far, after we got done with the introductory terms and all of that, we looked at 2 ways to present data. In a table with all the numbers spread out like that and all different things about them, and with a picture, a graph. So imagine that somebody was asking us, so how's the mood on campus this morning? Because that's what we measured. Oh, how's Connor doing? How's he doing? I'm not sure that Connor's person is here. No, not. Okay. I hope Connor's got a better mood today. I worried about him. But somebody asked you, what's the mood on campus today? You could show them the graph of that, and they'd be like, what is this? Or you could show them the frequency distribution table and they'd say, you've got to be kidding. I just want to know, what's the mood like? And what they really would love is, people are about a 5 out of 10. People love one number to describe a group. We love that. It helps. Cognitively, it helps us to anchor something in a central number. There's different ways that you could describe groups. We could say, oh, they varied from 3 to 10, or 3 to 9 rather, or 8, I think it was, right? So 3 to 8, they varied from 3 to 8. You can give them the low number and the high number. And sometimes that's what people want. And we call that the range. But most often what people want is what we call a measure of central tendency, some kind of middle number, some kind of a balance point. We use 3 different measures of central tendency to present data. 1, we can't do anything further, or 2, we don't do anything further with them mathematically. The other one shows up in many, many mathematical computations going going into further analysis. So the first two are, I'm going to do these one by one, so I'll wait to write them till I get them. But mode and median, we are only going to learn about them and not use them in any further calculation. But the mean is the third, and that we keep using for most of the term. Okay, so central tendency, let me give you a definition. It's a tendency of scores in a distribution to concentrate near the middle. Time for me to share my screen. I'm hoping that I can remember how to do it, so hang on. First thing I have to do is get to my screen. So give me a minute here. Then I find the right application. And then it offers to teach me something new, and I don't care about that. And then I have to find the right notebook. And then I have a blank page, and now I'm ready to share my screen. So I go here to share my screen. I'm getting it. And I go here to share my screen. I do screen mirroring. This is for those of you who like to hear your teachers think out loud. All right, blank screen. So I'm going to do something with a graph here to start us off. This was mood. And I think it was like up to 10. It started at 0, 5's in the middle, like that, etc. Like that. And then the number of people who had that particular mood is frequency, which went from 0 to, what was the highest frequency? Unmute.
I think the highest was 9.
Yeah, I think so too. Okay, 9. I'm gonna make that 10 just because it works well and it's close enough. Okay, this is sort of a 3/4 rule, sort of labeled graph of our data. And regardless of what it was, one way that data can turn out, if we had enough people, would be that most of the people scored right near the middle. That's what we call central tendency. And then it kind of fades out in each direction. There are times when it looks like that-ish. And this is an uglily drawn normal curve. That's what we call this. Normal curve. You might have heard it called a bell curve, because it looks like a bell, sort of.
Can you repeat the definition of central tendency?
It's the tendency of the data to, or tendency of scores in a group, either way, to be concentrated near the middle of the distribution of scores, near the middle of the data. So if you ask people questions on a scale of 1 to 10, it's a tendency of the scores to be many of them between 6 and 7-ish, or around 5, in other words. If the question was between 0 and 1, then it'd be the tendency of scores to be close to 0.5. And we have different ways that we measure central tendency. They have different uses. So the first one, the simplest one, is called the mode, and it represents the highest score in a distribution. So you get the one with the highest frequency. So that's the mode right there. You follow the line down, and whatever score this was, that's the mode. Unfortunately, we measured mood, so the word mood and mode are down there together. It's not helpful. The mode is the most frequently occurring score. In a normal curve, the data is balanced around the mode. So it looks like a bell because they're spread out around that high point. So the most frequently occurring score, if you have a frequency table, all you have to do is go down the column till you find the highest number under the column F for frequency, and then look across at your data column. So those of you who can still remember or have in front of you the table, what was the mode of our distribution?
Seven.
7, anybody else? Did anybody else get 7? Okay, thanks, Isaac. All right, so our mode was 7 in our case. So this is separate from the normal curve. This is a normal curve. But ours are, this is the mood data. I wrote mood instead of mode. Oh my gosh, hold on. All right, let's try that again. Mode equals 7. Okay, so the mode, all you have to do is look at the frequency column and go across to the data, and there's your answer. If you have just a loose group of scores, you haven't organized them yet, just count up the ones that look like they're the most and find the one that is, and that's your mode, the one that occurs the most often. So let's say that I have the group of scores 1, 1, 2, 2, 2, 3, 4, 4, 5. What's the mode? Anybody? I know 3/4 of you at least know the answer to this. So
2.
thank you. Thank you. I know you don't want to be the one that answers all the time, some of you, but we're going to need it to be able to move forward. 2 is the mode. Why? Because it occurs 3 times and none of the other scores occurred that often. Okay? That's how you do mode. So first put them in order because you're going to want them in order for the next one. But let's first talk about the advantage and disadvantage of the mode. Advantage, easy to find. Also, some people just want to know the mode. What's the most popular X? What's the most common Y? They want to know the mode. They don't want just any measure of central tendency. Sometimes people specifically want the mode, and so that makes it an advantage in that situation. Then we have the disadvantages. The biggest disadvantage is that it's the least useful for further analysis. We don't ever do anything with the mode. There's no formula that uses mode, none, that I know of anyway. Also, it's extremely unstable. If just one person had a slightly better mood, and instead of putting a 2 down for their mood, they switched to a 4, the mode jumps up to a 4 from 2. The mode can jump from at the highest to the lowest if just one person changes their answer sometimes. The mode can jump tremendous distances with just one person changing their answer. very unstable. Not a great measure of central tendency, unless your question is, what's the most frequent score? And that's all you care about. Also, another way to see mode, I forgot to tell you this, is just in a bar graph, you just have to look for the highest bar. And that's going to represent the mode. It's very easy to see and to spot. It's very, very easy to do kind of an off-the-cuff analysis of about the group, but you can't do anything further with it. Okay, I'm going to move on to the median. Median, MEDIAN, that's the next measure of central tendency. I have to change these data back again, hang on. The median is the score that separates the top 50% from the bottom 50% of scores. It's the center score, the one that separates the top half of scores from the bottom half. There's no mathematical formula to determine the median. The best way by hand to compute the median is to put them in order and count in from each side until you find it. So this is going to be, all right, I'm not going to show you because then I'd have to switch off of share my screen. But basically, let's do it like this. Okay, I'm going to get rid of the outside ones, and then I'm going to get rid of the next one in, and then I'm going to get rid of the next one in, and then the next one's in, and that makes my median 2. I took 4 of them off from each end, and the center score is 2. That's how you find the median. That's what a computer's doing when it finds the median. Computer be so fast you can't even, tell it's happening, has put them in order and counted in from each end and gotten the center number. All right, hang on while I erase these real quick. Whoops. All right, what happens, however, and this is an odd number of scores, so there is a center score. What happens if we have an even number of scores? Okay, we're going to count in from each end again and get to the center. So there's the outside ones, and then the next one's in, next one's in, next one's in. And now I have 2 to choose from. I don't cross them all off and say there is no median. It's tempting, but we don't do that. Instead, we take these 2 center scores and we get the center of them. So in this case, we take 2 plus 3 and we divide that by 2 to get the center one. The median is right there in the middle, 2.5. Numbers aren't always one apart. That's why there's a formula for median. The low number plus the high number of the 2 that you're working on. The low one plus the high one divided by 2. It's not always the number between the 2.5. It's always different. So if there's an odd number of scores, you just find the center score and that's the median. If there's an even number, you find the number halfway between the 2 center ones. Questions on how to find any of these so far? Okay. In that case, let me talk to you about advantages and disadvantages. Oh, wait, before that, I want to show you how to find the median in a normal curve. We're separating the top 50% from the bottom 50%. The normal curve is a symmetrical curve, right? It's a bell-shaped symmetrical curve. So that puts the balance point halfway up, which puts it right there. That's where, if you were going to fold this curve, you would fold it to get the top half separated from the bottom half, right along that line. So the mode and the median are in the same place. Same score. Because it's a normal curve, the mode and the median are in the exact same spot because it's symmetrical. Okay, median, how to find it. So the median is used in two main situations. One is when there are missing scores. So you have a whole big group of, say, 1,000 people that you've surveyed, and they've answered 10 questions each. And on question number 3, 3 people didn't answer it, or 5 people didn't answer it. The median will be better than what we would normally do as the mean. We'll probably do the mean anyway, so we can do analyses, but the median is actually a better representation of the data when there's missing data. It's almost always true. The other time that the median is a better representative of the data set is when you have what we call a very small distribution, few people, with extreme scores. So what that could look like is just a few people, but it looks like that. Say a class this size, and this would be exam scores where here's the number of people who got a score, and here's from 0 to 100. And it was an easy exam, or you guys are all geniuses and everybody scored up high except for like one person who hates this class and can't get it. And they're going to get it. Don't worry, they'll pass. We'll make sure. Everybody's going to make sure everybody passes. Even if you have to go knock on people's doors and say, wake the hell up, it's time for class. The other way it could go is like this. When it was a really terrible exam and almost everybody scored low. Except for these people who killed the curve. That's what it means to kill the curve. If everybody had been down there, it would look like this. Right? And then if these were the scores and nobody scored above a 50, we could all say that test was bad. It was a badly made test. The professor sucks. We have to fix things. But when you get some people scoring up in here, then you have to wonder why. And they killed the curve. And a lot of professors say, as long as a couple of people got an A, then I think it was a fair test, and we're going to include the grade in your overall grade. That's how that happens. Okay, going back to where we were. So the median is a fairly small distribution with extreme scores is when we use it, and when we're missing data. The median is not influenced by extreme scores. Here's what we mean by that. We're going to go back to this number list. Let me make a new one. Hang on. One, two, three, four, five, 7, 10. Let's say this was a 11 and 20. Let's say that this was a set of scores that you could score from 1 to 30 on your opinion about something. What's the median? I shall help with my highlighter. Halfway between 5 and 5 is 5. So the median is 5. Oh, class is over. We get an extreme score. Let's say somebody scored a 30. The mean would have changed a lot. The median doesn't shift at all. As long as you're talking about extreme scores out here, or way down here, then that doesn't shake the median at all. It is stable even with extreme scores. That's the last thing I wanted to tell you. When we come back in the next class, I will cover, oh no, this isn't the end of class. We're not an hour long. I keep forgetting how long this class is because we only changed it last year and my lectures are all set up to be 1 hour. So I'm going to keep going. Sorry about that. So the median is still 5, but if I change this number from 20 to 30, the mean is going to move, right? Okay, so it's stable. All right, moving on to the mean, which is what we're going to be using for the rest of the term. The mean is what we call the arithmetic average. So when we say average, what's the average? Most people are thinking mean. Once in a while, somebody's thinking median, but we don't, most of us think mean. And the way that we get the mean is the mean. So the mean could either be written like that for a population or written like that for a sample. But it's equal to the sum of the numbers divided by however many numbers. So Sam, your earlier question comes in right here. The sum of the numbers is the sum of X. That's what that little stuff, this sum of X means add up all the numbers, and over N is the number of numbers. So in order to get the mean for your sample, you would add up all the answers and divide by however many answers we have. And you have to be careful not to use the frequency distribution table to do it unless you know what you're doing, because you can't just add up all the answers. Some of them occurred more than others. You need to add up all of the 8s plus all of the 7s plus like that, right? So let's take a minute to get the median and the mean of the distribution of scores that you guys got and work on it. And I'll give you like a few minutes here and you can let me know. We'll see if at least 2 people agree on a number, then we'll know we're probably good.
Using those numbers right there,
No, using the numbers from the data collection on Mood.
oh, okay.
And I don't have them in front of me and I want to keep sharing the screen. So I'm going to let you guys, I'm crowdsourcing this. Do we have the median yet?
Would it be 2.9?
Did anybody else get 2.9 as the median? What were the 2 central numbers that you added up and divided it? It's not likely that it's 2.9.
Okay, then I probably
No, the
did it
median
wrong.
can't be 2.9 because the lowest score we got was a 3, right?
Oh yeah, I was looking at the mean, not the median.
It still
Or
can't
I,
be the mean because
looking
the
at,
lowest score we got was a 3. So something happened.
I was
Uh,
looking at something completely different. Sorry.
yeah, okay. Oh, you were probably using that other list that I had. Yeah. All right. Anybody else got the median?
I have a question.
Yeah.
So I have, like, for example, for a mood of 9, there were 5 people who answered that. So I would have to write down the number 9 5 times
Or you could
in
just
order to get that.
sub numbers. You can just say, okay, what is that, 45? So you could just write 45 plus and then the number of 8s and then the numbers like that.
Okay.
Oh, for the median. No, you're right. You're right. This is why I like the mean, because you don't have to screw around like this. Yeah, you'd have to write it out 5 times and then come in from each edge. I'm not sure your arms are going to be long enough for this problem.
And then for that too, does it matter like what way I go? Like I would have to start with the lowest. So number 3, I'd have to start with the mood of 3 and then work all the way up, correct?
Actually, you come in from each end. So you'd
Well, yeah, but would I have to have it like still in that order,
in
like,
that order, yes.
and then starting? Okay.
Yes. So in other words, the median's a pain in the neck when you have a bunch of data. Just remember that as another reason why we like the mean. Has anybody computed the mean yet?
I have both of them.
What you got, Sam?
The median is 7 and the mean is 6.73.
Anybody else get either of those? We're gonna wait for verification. 7 and 6.73 is what we're waiting for. Jack, what you got?
I got the same thing.
Okay. 7. You put all the numbers down, you went in from the edges, and 6.73, you added up all the answers and divided by however many people we had. Okay, notice how close all of these numbers are. This is very close to a normal curve. On a scale of 1 to 10, our 3 measures of central tendency only varied by less than 0.3. It basically looks like the picture here. But in a perfect normal curve, not only is the median and the mode in the center, but then the mean is too, just like what we're finding. So this is the mode, the median, and the mean in a perfect normal curve. They're all 3 in the same place at the high point on the frequency axis. And to find it, don't give the answer frequency, because that's a very common mistake. To find what the actual answer is, you got to go down to the data column, to the data axis. So the highest frequency leading to the corresponding X. Who's got a question so far about what's going on? Who had no idea and wants more opportunities to practice median? How about mean? I see nobody saying I want more. Okay, how about mode? All right, so it sounds like you guys get the concept and you get the normal curve. Let me give you some more details about the mean now. The mean has properties that for some reason you should learn. They come up later, but we're now about to get a little bit more complicated for those of you who are having trouble thinking about the logic of this instead of just the math. The mean is often called the balancing point of a distribution. Some are above and some are below some of the points, some of the data. So we can call them positive differences from the mean and negative differences from the mean. In other words, let's take the number set 1, 2, 3, 4, 5. Okay. Yeah. Sorry. For some reason, it took me to the wrong notebook. And now I have to go back to the notebooks and find it again. It's really ridiculous. All I was trying to do was erase. Okay. Forget it, it won't let me draw it. I've got to start over here. This is just data that we're collecting. Okay, 1, 2, 3, 4, and 5. Those are our possible answers. There's the frequency of answers. Let's say that everybody had the choice of how many servings of caffeine they had today, and one person had 1, one person had 2, one had 3, one had 4, and one had 5. Okay, so coffee. We would get a straight line, right? We would get, if this is one person said the answer and 2 people, etc., then basically ours would look like this. One person for each answer. That's a straight line graph. Just so that you realize that I just wanted to draw that for you just to see how that can happen. If one person gives every answer, each answer has one person, then you get a line. Okay, what's the mean of this distribution? 1, 2, 3, 4, 5. 3, correct. What's the median? Somebody unmute, please.
3.
3, okay. Because the center score, 1 and 2 are below it, they're negatively different, and 4 and 5 are above it, they're positively different. Okay. If we add all of the positive and negative differences from the mean, the result will be 0. That's how the mean is derived. So the positive and negative differences, let's start at 5 and work down. So 5 minus 3, 4 minus 3, 3 minus 3, 2 minus 3, and 1 minus 3. That's what it's talking about, all the differences. And we have to remember to use a negative number if the difference is negative. So 5 minus 3 is 2, 4 minus 3 is 1, 3 minus 3 is 0, 2 minus 3 is -1, and 1 minus 3 is -2. And when you add all those up, you get 0. That's a property of the mean. The sum of all of the deviations from the mean is 0. The sum of the deviations from the mean equals 0. There's actually a way to do that in a formula. It looks like this. This means the sum of, this is a score, that's a mean. So far we've got the sum of the deviations from the mean equals 0. That's one of the properties of the mean. The next property of the mean is just irritating. People don't like to learn it, but you have to learn it anyway. 1, 2, 3, 4, 5. Those are your numbers. I like to start with nice, simple numbers to explain stuff like this. Okay. I'm going to write this out. The sum of the squared deviations from the mean is smaller than the sum, this is horrible, of the squared deviations from any other number. There's a way to write that. It looks like this. The sum of the squared deviations from the mean is less than the sum of the squared deviations from any other number. I'm not sure how I'm going to represent the number, every other number. I'm just going to go X question mark. That'll be any other number in the data set. For those of you who prefer the symbolic language of math, there you go. So I know that that's a complicated bunch of words. The sum of the squared deviations from the mean is smaller than the sum of the squared deviations from any other number. So I'm just going to show you what we're talking about. We go back to these deviations from the mean right here. And we're going to square them. The sum of the squared deviations from the mean. Okay, so these are deviations. These are deviations squared. And 2 squared is 4. 1 squared is 1, 0. 1 squared again is 1, and negative 2 squared is 4. And we get that number, and what we get is 10. Okay, so I'm taking that 10 to this page over here. The sum of the deviations from the mean was equal to, what was it? Just the regular difference, 0. Oh, duh. And the sum of the squared deviations from the mean is equal to 10. Now let's test this. Let's take any other number like 4. What this property is saying is that when we do this, we're going to get some number bigger than 10. If we use 4 or 5 or 2 or 1, we're going to get some number that's going to be bigger than 10, because 10 is the sum of the squared deviations from the mean. All right, so, and we did square deviations from the mean back here. All right, now let's do it with 4. So 5 minus 4, and we're going to square that. We're going to get the deviations, and then we're going to get the deviation squared. 4 minus 4, 3 minus 4, 2 minus 4, and 1 minus 4. See why I use small numbers to begin? So 1 and 1 squared is 1. 4, 0, and 0 squared is a non-number, but we're going to call it 0. 3 minus 4 is negative 1, and we're going to call that 1 squared. 2 minus 4 is negative 2, and we're going to say that the square is 4, and 1 minus 4 is negative 3, and the square of that is 9. And we're going to find the sum of the squared deviations from the mean, which is this column on the right. 1 plus 0 is 1, plus 1 is 2, plus 4 is 6, plus 9 is 15. 15 is less than 10. I mean, is more than 10. And when you do it with 5, you're going to get an even bigger number. And when you do it with 2, you're going to get 15. And when you do it with 1, you're going to get whatever you did with 5. They're all going to be greater than 10. That's what this property means. Why do we care? I don't know. I honestly, it's part of calc and pre-calc. It's not really part of statistics, except it's important to know the properties of the mean while you're learning what the mean is, in case you go further in math. And I'm thinking of who's in this course, and as far as I know, none of you are going on in the math department, but still supposed to learn it. It's part of every stats class all around the country.
Is this going to be on a quiz?
I'm not going to put that on the quiz. No, I hate it.
Oh, okay. All right, good.
I will put mean, median, and mode and other stuff about it on a quiz, but I won't put that on one. Okay. So when we compare measures of central tendency, the mode is just used when we're describing data, when people want that. That's all I have to say about the mode. The median we use, just as I said, when we have I already said this, a small distribution that's got some extreme scores or missing data. The mean is the most useful of the three. We use it a lot. It's based on all the data. The mode, if we change one score to an extreme score, the mode doesn't shift. The median doesn't shift, but the mean representing all the data shifts tremendously. What if instead of 1, 2, 3, 4, 5, the mean of which is 3, it was 1, 2, 3, 4, 20. 1 plus 2 plus 3 plus 4 plus 20. Is that sum 32? So 32 divided by 5 is 6 point something. The mean went from 3 to 6 point something by changing an extreme score, better representing all the data. The mode wouldn't have changed, the median wouldn't have changed, but the mean does. Oh, by the way, I forgot to tell you, when there's no data that occurs more than others, there's no mode. Sometimes we have no mode. There's no mode in this 1, 2, 3, 4, 5. Each score only happens once. I'm going to get to what happens when we have more than one mode here in a little bit, because I'm going to talk about shapes. The most important use of the mean is to use a sample mean to estimate a population mean. Remember, if we wanted to know the IQ of all the left-handed people in EC, that's a population, but I might only get a sample of 30 students, and that's a sample, and I could use their mean to estimate the population mean, because I can't get to a population.